So next lecture is by Tobias Kaiser from Passau.
Thank you very much. Thank you very much for inviting me to this great conference, to this great place. So my talk is about periods, power series, and integrated algebraic numbers. Here, periods, these are period numbers, not period functions. And I'm very happy to Tom Scanlon for this very nice tutorial, because this will be also very helpful for the talk, what is following. We start with the motivation. So period numbers play a fundamental role in transcendental number theory and arithmetic geometry. Well, I don't have to tell you about that. For example, they arise in pairing, singular homology, and algebraic de Rham homology. You have here sigma is a cycle, omega is an algebraic differential form. You integrate it and you obtain a period. A period can be formulated in a more elementary way, not at this high level. Here I give the definition of Concivis and Sage. What is a period? A period is a complex number whose real and imaginary parts are values of absolutely convergent integrals of rational functions with rational coefficients over domains in R to the n, given by polynomial inequalities with rational coefficients. So in other words, I integrate a function, semi-algebraic over Q, over a domain, semi-algebraic over Q. In the following, we consider periods that are real. This is no problem, because we can always separate real and imaginary part. And then, such a real period is given by integral of a semi-algebraic function over Q on all of R to the n, which is absolutely integrable. So this is not weaker. One might think, where is here the domain? Well, we can always move the domain to the function by multiplying with the characteristic function. Okay. Here are examples for periods. For example, pi. Pi is a period because it's just a volume of the unit disk in the plane. For example, the logarithm of 2, logarithm of natural numbers, given by this integral of a semi-algebraic function defined over Q. Or, more complicated, zeta function at natural numbers. Here is a description of theta 3 in terms of an integral. But here you see any dimension, and integration any dimension, and this makes it very hard to compute such periods. And so it's not much is known about periods, so it's not known whether the Euler number E or the Euler constant gamma are periods. So what is the Euler constant? You have the logarithm, which is the antiderivative of 1 over x, and you compare it with the step function. And this limit exists as n tends to infinity, and this is the Euler constant.
Even more depressing, we don't know if 1 over pi is a period.
Yes. Yes. So periods are defined by interaction of algebraic geometry, so semi-algebraic over Q, and analysis, where is analysis coming from? Integration. And integration is not a first order compared to differentiation. And this makes it hard, really. So what are the goals of my talk? Describe periods in a more formalized way, and define new countable number systems in an analytic geometric way, so coming from homonymality, capturing the important mathematical constants. What is the starting point? Well, in the following way one gets periods. I take a real power series which is algebraic over the rational polynomial ring. So a power series which is semi-algebraic over Q. That's the same. I take its formal antiderivative. We have a power series, we can take its formal antiderivative. Algebraic power series are convergent. Taking the formal antiderivative, we have the same domain of conversion. And now I evaluate such a power series at a rational point in its domain of conversion. Examples. We start with the logarithmic series. So this is log of 1 plus x. Has radius of conversion 1. 1/2 is contained in the domain of convergence. And so log 1/2 is this period, is given by logarithmic series, which is the antiderivative of 1 over 1 plus x at these rational points. And log of 2 is just the negative of log 1/2. Next example. I take the arcsine series. So if the sine inverse function is the arcsine. Sorry, that's true, but why is arcsine? Well, the derivative of arcsine is 1 over 1 plus x squared. So we have an antiderivative of an algebraic power series. The radius of conversion is again 1. I evaluate this at p over 6. At 1/2. This gives p over 6. And again, I have such an antiderivative, formal antiderivative of an algebraic power series at the rational point.
So this way you can't get all periods this way, right?
In some sense, yes.
All period,
This is my result.
but just one integration?
No.
You'll need to repeatedly integrate.
It's coming. So next, I want to introduce the setting that in this process, in this iterator process, we obtain all periods. So we follow this approach. So we start with the power series, which are algebraic over the rational polynomial ring, the same as the power series, which are semi-algebraic over Q. We call them simply algebraic power series. We close them under taking formal antiderivatives, iterated, and nearby algebraic and geometric operations. What do I mean? Main definition here. We consider the smallest class of rings of power series which contain the algebraic series and are closed under taking reciprocals, rational polynomial substitutions, rational translations, and formal antiderivatives. So these are these algebraic geometry operations. Well, I think they're not rather natural.
Do you allow poles?
Sorry?
Do you allow poles? So what do you mean by reciprocals?
I will explain it. So reciprocals indeed is only defined for power series we do not manage at the origin. And then I take the 1 over. For example, the reciprocal of 1 over 1 minus x is of course the well-known geometric series. Then rational polynomial substitution. I have a power series in my process, and I plug in polynomials over Q vanishing at the origin. So we replace the coordinates, a rational polynomial vanishing at the origin. For example, if in my geometric series I plug in x1 plus x2, I get this power series in 2 variables. Rational translation. Well, I have convergent power series. And I know if I have a point in the domain, I can develop my conversion series at this point again in a power series. And if I have a point in the domain of conversions with rational coefficients, then I'm allowed to develop my given power series I have obtained in a process at such a point.
So only when you have also rational coefficients the other point.
All rational points, yes. So here, for example, if you have the geometric series, you develop it around the point 1/2, you obtain this power series. And formal antiderivative, as before, this is the formal antiderivative we know of power series, but note that we have in general power series of arbitrary many variables, not only one variable, but arbitrary many variables, and then you're allowed to take formal antiderivative with respect to any. For example, the formal antiderivative of the geometric series is of course this here.
Great. And in the definition you said you have a class of rings, it's just because you have for every
n.
variables?
For every n, yeah.
But he has these rational substitutions that involve several variables, so they're connected at different times.
Of course,
Right.
There you are. Of course. Okay. And we call the series obtained in this way the integrated algebraic power series. And we obtain the following results, so contributing to your questions. First, theorem A. Well, I have this class, starting from the algebraic power series, and then closing under these operations, geometric algebraic operations. Then, well, I consider all the coefficients appearing in my integrated algebraic power series. Then these coefficients, they form a countable real closed field. And we call this the field of integrated algebraic numbers. Now,
So I'm not sure if I followed one of the axioms correctly. When you make a substitution like x plus 1/2,
yeah,
you do it only when you have rational coefficients around 1/2?
No.
no. I only, so the important thing is that this here has to be rational.
Okay, yeah, because you said with rational components, I wouldn't.
Yeah, because in general I have x1 plus a1, x2 plus a2, x3
Okay, so,
plus
okay, the
a3.
components and not the coefficients. Okay, that was what was
Okay, yeah,
Yes, thank you.
okay. So, the coefficients, they form a real closed field, which I call the field of integrated algebraic numbers, because algebraic power series, the coefficients are the algebraic numbers. Now I have the integrated algebraic numbers, I call the coefficients integrated algebraic numbers. And now contributing to your question, a period is an integrated algebraic number. So in this way, I obtain all periods, but of course, much likely much more, because it's easy that 1 over p is an integrated algebraic number. Why I am allowed to take reciprocals, for example. So, what do we have? Everything is more or less encoded in power series. Starting algebraically, and then doing this finitely many algebraic geometric operations. And the analysis is somehow reduced to the evaluation of power series at rational points. So the integration is completely moved to formal integration. Okay. So, what about theorem A? The central observation is here the following: that this system of integrated algebraic power series has very nice properties. And what I call it's a convergent analysis system. So first I explain what I understand by a system of convergent power series, a convergent system. And then I explain what I understand by a convergent analysis system. So what is a system of convergent power series? So for each n in n0, I have Sn consists of power series in n variables. And Sn should be a subring of the ring of real convergent power series, which I denote by the following. The next is more or less for convenience that my rings Sn are closed under permuting variables. That's not really a problem because, for example, algebraic power series have these properties and so on. So all the natural classes have these properties. And for notation reasons makes life easier because I can always express with respect to the last variable. And S0, which I denote by k, small k, this is a subfield of R, and all the coefficients arising here should be from k. And of course, also the polynomial should be in there. Okay. And this k is called the coefficient field. So algebraic power series, they have the coefficient field algebraic numbers. Integrated algebraic power series, they have the coefficient field integrated algebraic numbers. And what is a conversion system? Well, I'm working in a setting not of formal power series, but of conversion power series. And so we have here the property of translation. If I have a function in my system and a point in the domain of convergence which has coordinates in my coefficient field, then I can develop my power series around this point. Okay.
But then following finite sequence, you can get any germ of an analytic attenuation, right?
Yes. I really want to have, let's say, always the maximum. So I always want to consider the complete domain of convergence.
Yeah, but I mean, even if you have to go, or even if it's not the domain of convergence, you can start like
Ye-
following
yes,
a sequence
yes,
and
yeah,
see
yeah, yeah,
the
yeah.
entire Riemann surface of the function.
Something like this, but at least, but all of my power series are always, let's say, local. They are defined on this domain of
Yeah.
convergence. Yep. So it's important here that I'm not working on some neighborhood of zero, but I really need on all of the domain. Okay, and what is a conversion analysis system? It's a conversion system, just have been defined before, such that the following holds. Well, again, we are allowed to take reciprocals of power series not vanishing at the origin. Then the next one is also easy restriction. Some of the coordinates we can replace by 0. No problem. Closed undertaking derivative. So we have a power series, conversion power series. The derivative is again a formal conversion power series. We need here that the derivative is again in there. And now we need some complexification. So what do I mean by this? If I have a real power series, conversion real power series is of course also a convergent complex power series. So it does not only converge on a neighborhood of 0 in R to the n, but also in C to the n. So I can plug in complex variables. So I have now 2 to the n real variables, x and y. Now I separate again. These are now then real power series in 2n variables, and they should be also in my system.
If you just walk to begin with of a complex something of the complex numbers, would you get something different or?
Well, first I'm in a setting of omnimality, so I want to start real. Yeah, but should be no problem. Just go add I to the field I have, then it should be the same now. And integration, I allow formal integration with respect to any variable. Note that we have permutation of the variables. So that's what I'm calling a conversion analysis system. And the following implications hold. One can show, if I have a conversion analysis system, I obtain what's a so-called convergent Weierstrass system. What is a convergent Weierstrass system? So Tom also had this in his talk, these notions. So it's a conversion systems where I have Weierstrass division and preparation in my system. And then by old results of the Neff and Lipschitz, in a Weierstrass system, I have arbitrary substitution, I have compositional inverse of series, I have implicit series, and so on. So what is now a new feature compared to literature? So the Neff and Lipschitz, they consider formal systems on any field of characteristic 0. So far in the literature, systems of convergent power series on the reals. But now I'm working on subfields of the reals. So starting with the algebraic numbers and doing closure operations, I change my field. Examples. The system of algebraic power series is a convergent Weierstrass system with coefficient field A of real algebraic numbers. But it's not an analysis system because I do not have formal integration. But my system of integrated algebraic power series is a convergent analysis system with coefficient field by definition, which I called IA, of integrated algebraic numbers. So here one has to do some work. Why? Let's go back. This is done by our setting. This is also no problem. Derivative, we don't have formulated in our definition of integrated algebraic power series. One has to prove this, that this holds. And one has to prove that the complexification holds. This is again by our setting. Okay.
In particular, it's also a Weierstrass system.
Yes. Yes. This is a Weierstrass system. But so we have in our analysis system is more. And there is a observation that you have a conversion Weierstrass system on a subfield of the reals, then this field is real closed. Not too hard to show. Because we have by the Neff-Lipschitz this inverse functions. So if a polynomial which has a root in the reals, this root has already to be downstairs in the field. And this gives theorem A. Why? Our system is a conversion analysis system. Conversion analysis system is a conversion Weierstrass system. And this gives theorem A. Okay. How about theorem B? Now omnimality comes into the game. Tom has defined or given in his tutorial the notion of a restricted analytic function. And I do now the same. So what is a restricted integrated algebraic function? Is the following. I take an integrated algebraic power series, conversion of the neighborhood of this closed unit cube, but only on this field. And outside, I extend it by 0. Okay. So this X only has components from this countable field. And let REA be the structure over the field IA by these restricted integrated algebraic functions. Now we want to understand this function. We introduce some languages. Natural, as in the case of AN, analytic RAN structure. So L is the language of ordered rings. I extend it by symbols for every restricted integrated algebraic function. I add a symbol for the reciprocal, x is mapped to 1 over x. And I finally add symbols for every power function with rational exponent. Then following, extending the work of the Neff and Van den Dries, Mark and McIntyre, the paper which were mentioned by Tom, we get that the following holds for the structure, for this structure on the countable field of integrated algebraic numbers. First, the structure is omnimal. It has quantified animation in this language when I add reciprocal. And functions definable in this structure are piecewise given by terms in this biggest language. So the final function can piecewise also, well, the more or less compositions of polynomials, integrated, restricted integrated algebraic functions, and powers with rational exponents. Okay. Note that one can use, so in this proof there at some points there are compactness arguments. Because I'm working on the reals. We are working on a countable real closed field. We do not have the compactness arguments. That's why I need that I can do everything on the whole domain of convergence. So it's not enough to work on small neighborhoods around 0. I have to cover everything. Good. But now, remember we are thinking of periods, there is integration needed. And now more comes into the game. So, integration in omnimality, the fundamental result is by Lior-Rollard, Comte Lior-Rollard, about understanding parametric integration of functions definable in RAN. And this is based on Liot-Rollat preparation. Namely, the next, so following Comte, Liot-Rollat, and also the extension by Dan Miller. Dan Miller extended this to, let's say, Weierstrass systems on the reals. We showed that this structure allows Liot-Rollat preparation. So it's different style of Weierstrass preparation. What is Liot-Rollat preparation? We have a function in variables x and a singular variable y, and piecewise I can prepare my function with respect to the y variables. How does it look like? So in Weierstrass preparation, you have something powers of y. Here you need a little bit coordinate substitution. So I take this translation, y minus theta x, where theta only depends on the first variables. Then I have here power with rational exponents. I have a prefactor depending only on x. And then here I have a unit. So what does unit mean? Unit means away from 0, away from the infinity. And the unit can be controlled. Namely, here again functions of this form, finitely many, and I plug this in to a power series in our system, which is away from 0 and infinity. So here, U is a restricted integrated algebraic power function or power series, not vanishing on this compact set, so therefore it's bounded from above and below on this compact set. So here now on the reals, this makes no difference. Then all this takes values in this unit interval, and the coefficients are the exponents are rationals. So this is the Liot-Rollat preparation. Yep.
Yeah, no, yeah, of course, you mean the full Liot-Rollat preparation, right? There's an extra very important condition about, you know, on the cell, the size of y minus theta x should be comparable to the size of.
Yes, of course.
So
Yeah. I have the full, but for technical details.
Yeah.
So this is the qualitative.
You get the full.
Yeah. But I have the full. Yeah. And then, as stated, they used Liot-Rollat preparation to obtain results on integration. And we can follow this path. Now we can consider integrals in our structures with parameters. So what is the setting? I have here a function in our structure, x parameters, y is now not a single variable anymore, arbitrary variety. So, what to think of? X is a parameter, I integrate with respect to y. What do we have? The set of all parameters where this function is integrable with respect to y. This is again definable. Well, here one may think, why is it talking about integration on countable fields? So what is, well, but this have of course all a canonical lifting to the reals, interpretation of the reals, and there we have the integration. Okay. So the set of parameters is again here. And now on this set, I have this parameter integral. Yep.
Okay, integrable means absolutely integrable.
Yes. There's a Lebesgue theory it should be. Okay. So on this set fin f, I have this parameter integral. And this can be described in a very nice way. Namely, there are functions definable in my structure. Here general ones, here positive ones, such that this parameter integral is given as a sum of products of my definable function and the logarithm of definable functions. And for this, I really need analysis system. So for Weierstrass system, at least you do not know how does it work. Okay, so to understand integration here, one only has to add the logarithm. So this was the nice result by Comte, Leon, Rollard, and here we can achieve the same.
And surely this is not true for every Weierstrass system, right? It wouldn't be true for just the algebraic Weierstrass system.
That's why I said, so it's true for conversion system. Oh yes, you were right, completely right. There we have a counterexample. Okay. And now going back to periods. Well, in periods, we do not have a parameter. So a period, so far the result that a period, well, is a sum of products of integrated algebraic numbers and the logarithm of integrated algebraic numbers. But the field of integrated algebraic numbers is closed under the logarithm, which is also not hard to show, because the logarithmic series is in our setting. So this gives theorem B. And note that the previous theorem describes also families of periods. So let's say if I start here with something semi-algebraic over Q, then I have here a parameter family of periods, then they also have this nice description. Maybe this can be of some help somewhere. Okay. Next one, next step, what I call exponential integrated algebraic numbers. Well, we have seen that the field of integrated algebraic numbers is closed under the logarithm because we have the logarithmic series in there. But recall, the integrated algebraic power series, they form a analysis system. Analysis system implies Weierstrass system. In Weierstrass system we have compositional inverse. So we also have the exponential functions. And this gives that the field of integrated algebraic numbers is, so this countable field is also closed under exponentiation.
But not kind of uniform.
So the exponential series is in my system.
Ah, right.
Yep. And now, so I can expand the Ullmann structure by the exponential function, and which is again a structure on my countable Webflows field downstairs. And then following and extending again the paper of Van den Dries, Mark and McIntyre, this Engels paper Tom mentioned, the following holds for this structure on the field of integrated algebraic numbers. It is omonimal. It has quantified elimination in the language when I add exponential and logarithm. And again, functions definable in here are piecewise given by terms in here. Also quite nice that at least piecewise the definable functions are compositions of something I know. So it's built up of power series in my setting, exponential, logarithm. And now a definition. Exponential integrated algebraic number is the integral of a function, of a integrable, absolutely integrable function definable in here. So a period was a definition of a function, semi-algebraic function over Q. That's the same as we have just shown before. It's the same that, so it's not, sorry, no, not the right thing to say. But here, that's my definition. An exponential integrated algebraic number is the integral of a function definable in here. And what is the result here? Well, this exponential integrated algebraic numbers, they give a countable ring, of course containing the periods, but also containing the so-called exponential periods, and also the Euler constant gamma. What is an exponential period? It's a pity that Philip is not here anymore. So they have just written, I think, 2 papers about exponential periods. There are several notions of exponential periods. They have shown that they can use, for their purposes, they use a definition which works also in my setting. So what is an exponential period? This is given by integral of exponential of a function f, semi-algebraic over Q, but now this can also take values in the complex field, times another semi-algebraic function over Q. And important, now I follow the definition of Annette Huber and Philip. In their definition, the imaginary part of f can be bounded, and that's why I'm in the omnimal business.
It should be absolutely integrable or something?
As always.
And still, even though it's absolutely integrable, they need the imaginary parts to be bounded?
They show that for their purposes, it's enough to work with this. Okay. So here, overview.
Sorry,
Yeah.
how does gamma get in there?
Gamma has some so even in Wikipedia, so there are some quite basic integral representations of gamma. So not too hard.
Right.
Yep.
Okay.
Is there any familiar constant that isn't in this ring now of the exponential integrated algebraic numbers? Can you give any classical constant that isn't there?
I hope that not.
Okay.
Okay.
How about you
Hmm?
How about you
Well,
No, yeah, natural constant.
yes. So here's an overview. So I have omnimal structures, uncountable fields, and what do I get when I integrate absolutely integrable functions in this? The structures integration. So I start, what is the structure? Universe, where does the structure lives on? I apply integration. Which numbers do I get? Well, first structure, semi-algebraic sets and functions over Q. This is the same as the structure given by the restricted algebraic power. functions. Here, this lives on the real algebraic numbers. When I integrate, by definition, I get the periods. Now I start with my integrated algebraic series, so with restricted integrated algebraic functions. This structure lives on this bigger countable real closed field.
Well, you think it's bigger. Oh, no, that's
No,
definitely,
this
that's
is clear.
definitely bigger.
This
Sorry,
is clear
yeah.
because pi
The
is in
end
here.
result, the end result for all we know could be the same.
If I integrate here, I stay in this. This was the previous theory.
Could it be that it's generated by the period? This field?
Yeah.
How much bigger is it?
No, it's not generated. So I suppose that it's really bigger. Because
We don't know. It's hard to prove that things are not.
yeah, of course,
Very
but
difficult.
at least you see I have power series, I have to evaluate the iterational points and so on. So okay. Now my third Omenma structure. So integrated algebraic series plus global exponential. Structure again on this countable field of integrated algebraic numbers.
Yeah, you do.
If I take integrals, by definition what I call exponential integrated algebraic numbers. And now about number systems, to show you the final picture. Well, the basics is the field of algebraic numbers. Then I've introduced this field of integrated algebraic numbers. I have this ring of periods, I denote by P. I have this ring of exponential periods in the sense of Harbaker and Huber. And I have introduced this ring of exponential integrated algebraic numbers. And here is the very colorful picture at the end. It's a little bit in the direction of Christmas or Hanukkah. So here we start. So this is the classical part. We start with the algebraic numbers. Then we have the periods. We know that pi is a period. 1 over pi we don't know. E we don't know, but I think people think that
No.
it's not. And the same for gamma. Now the exponential periods, E isn't there, but the question is gamma there. And now this new path, let's say, P and E are integrated algebraic numbers. Gamma I don't know. But now this integrated algebraic, exponential integrated algebraic numbers, we have P, E, and gamma. This is about constants, but I think the really interesting stuff is that these periods, families of periods, now is connected to nice Omenma structures. So really nice with all this quantifiable animation, piecewise given by natural terms, and all on countable fields. Thank you very much.
Question?
This picture, what is the relation between exponential periods and integrated algebraic numbers?
No. I don't know.
So do you know if the integrated algebraic numbers are the real closure of the periods or not?
I don't think so. But no, but still these are really the hard problems. Yeah.
So you can show that the integrated exponential structure is closed under integration in the same way that the integrated algebraic one was closed under.
Not at all, because that's missing the result on integration momentality. we do not know how to deal with exponential function when integrating.
Do you get the Lyon-Roland log exponential preparation? I know it's not good enough for integration.
Yes, but we can get this. This is no problem. Yeah.
And my final question is, so let's say I give you a period.
Yeah.
So I mean, it follows from what you said that it can be written as in a simple way using this integrated exponential stuff.
Yeah.
Sorry, integrated algebraic stuff.
Yeah.
So what would it take to actually give a bound, to show how you can write it? Is it only Lyon-Roland? So suppose I told you that that Lyon-Roland you can do effectively and you know how many pieces. Would it say that you can take any period and express it kind of effectively in this ring? Or are there some other sources of ineffectivity? And Lyon-Roland has some compactness argument.
Oh yes. So you mean to extract?
I mean, let's say I gave you a period of some
Yeah.
polynomial of
Yeah.
degree 10.
Okay.
So
Yeah.
do we know that, well, you can write it in this way with some expression of length?
So I give you the power series and so on, and so good point. Yeah.
Do you think that there is another? So I mean, where is the deep ineffectivity? Is it Lyon-Roland or something else? Maybe it's a strange question for a model theorist. You're not used to think about effectivity.
Yeah, ineffectivity is in your talk. I think it's Liot-Rollat preparation to find the cells, where this Liot-Rollat preparation holds, and so on. Yeah.
Thank you.
So, for computing a pair, somehow, I mean, you integrate functions under the assumption that they are absolutely convergent.
Yeah.
So, I mean, is there a way to take into account when functions are not absolutely convergent and you just throw them away?
Well, first of all, in the one-dimensional case, there should be no problem also to deal with both cases. But in the higher dimensional cases, it's always quite unclear what does it mean not to be integrable but not absolutely integrable. Because usually we are doing the back integral, and then integrable is the same as absolutely integrable.
We know Galois group acts on the algebraic numbers, or maybe you usually real algebraic numbers.
Yes.
Complexification of it.
Yeah.
Does it act on any other of these sets?
Yeah, well, so we know that this is a real closed field. That's so.
So on the complication of it.
Yeah, well, you know, with a real closed field, you add square root of -1, you get a algebraically closed field.
So does Galois of the rational, does the Galois group of the rational numbers act on, it acts on A with I, but it's,
Here, but it's not contained in cube R.
okay.
Yeah. Because here we have transcendental numbers, for example, pi.
Can I ask, have you thought about this in the function field framework at all? Do you get anything new beyond, I mean, I assume you do, but beyond the exponential function and doing that?
I am not,
No.
too less knowledge on this.
Let's turn the speaker again.